Welcome back. I hope you have remembered what is the derivation of condition of tangency and you remember the condition of tangency as well. Now in this part I am going to tell you about how can we dot two tangents or a pair of tangents from a point outside. I am also going to discuss one of the important part, that is the equation of normal and condition for what is the maximum number of normals that can be drawn from any point to the ellipse. So let's start.
Equation of pair of tangents. Now, if there is any curve, for example, in this case we have ellipse, if there is a point outside, so we are going to draw tangents to that curve from the point outside. So, the equation of pair of tangents, that means that there can be two tangents that can be drawn from a point which is outside to the ellipse. So the equation of those two tangents, combined equation we are talking about, because we are talking about pair of tangents. So equation of pair of tangents from x1 y1 which is outside the ellipse. So remember the point is outside the ellipse. This is given by t square is equals to ss1. You can see here that if this point is outside, then these are the two tangents which can be drawn. Their combined equation is given by t square is equals to ss1. But what is t, s and s1? The t, s and s1 respectively are these. T is the equation of tangent in normally the equation of tangent t is equals to 0. S is the equation of curve. S1 is the equation of curve when you have satisfied the points x1 and y1. So this is the combined equation of pair of tangents. Now we'll do a question on this. We need to find the locus of point of intersection of pair of perpendicular tangents to his ellipse. So the question is saying that from this point h comma k, two tangents are drawn to the ellipse and they are perpendicular to each other. So you need to find the locus of this h comma k. Now look how we are going to find it out. One of the method is to find out the equation of pair of tangents from h comma k and then use the direct result that what if two straight lines are perpendicular to each other. A more easy method is using the general equation of tangent in slope form and solving for m. What I'm saying? Look here. We know that equation of tangent is y is equals to mx plus minus square root of a square m square plus b square. Now this equation passes through h comma k. So what I'm going to do, I'm going to satisfy this point. K is equals to mh plus minus square root of a square m square plus b square. So now we are going to find out the locus of h comma k. If I bring k minus mh to this side and I keep this to the other side and I'm going to do whole square to eliminate the root. So what I'm going to get, k square plus m square h square minus 2khm is equal to a square m square plus b square. If I simplify this equation by making it a quadratic in m, look how it transforms. M square of h square minus a square minus 2khm plus k square minus b square is equals to 0. Now clearly this equation is going to have two roots which are m1 and m2. m1 and m2 also corresponds to those two straight lines or those two tangents which can be drawn from h comma k. If both the straight lines are perpendicular, that means we know from the condition of perpendicular that m1 into m2 is minus 1. And m1 into m2 is also the product of roots. So product of roots is c upon a, that means k square minus b square divided by h square minus a square. This is equals to minus 1. That means if I simplify it, then I am going to get h square plus k square is equals to a square plus b square. Or if I replace h comma k with x and y, then x square plus y square is equals to a square plus b square. This equation represents a circle. So you can see that this is the dotted line, this is the circle. So it's the locus. The locus is a circle of this h comma k. Now we'll move on to what is the director circle. So director circle is again the locus of intersection of perpendicular tangents. The locus of point of intersection of pair of tangents that are perpendicular to each other is called director circle. The equation of director circle, as we derived in the last question, x square plus y square is equals to a square plus b square. So remember, this was h comma k in our previous question whose locus we derived. Now we'll move to equation of normal. Now suppose that you have any point x1 y1 and you want to find out equation of normal passing through that point. How can we do it? Recall the part in which we derived the equation of tangent. How we derived it? We found out it's dy by dx because dy by dx gives us the slope of tangent. If I do minus dx by dy, that is, I invert it and I apply a minus sign, that will be the slope of normal because tangents and normal are perpendicular to each other. So by the same concept, you can see that the equation goes same, y minus yy into x minus x1. This thing is actually minus dx by dy because dy by dx is slope of tangent. So minus dx by dy will be slope of normal because m1 m2 is minus 1. If you simplify this equation, you will reach here. So this is a very simplified form. X minus x1 divided by x1 by a square is equals to y minus y1 divided by y1 by b square. What I can do is that I can substitute x1 y1 in terms of a cos theta and b sin theta. Why? Because x1 y1 lies on the curve. So any point that is lying on the curve, I can write it in parametric form as well. So if you replace x1 y1 by a cos theta and b sin theta, and if you again do some manipulation to put it into some correct form, you'll end up here. So this is the simplified equation of normal through an ellipse in parametric form. Remember, parametric form. Ax sec theta minus by cosec theta is equals to a square minus b square. Now let's check our concepts. So we need to prove that the straight line Lx plus my is equals to n is a normal to the ellipse x square by a square plus y square by b square is equals to 1 if it satisfies this condition. So we need to prove that this is a normal to this if it satisfies this condition. Now if we go back to the previous slide, you can see that we don't have as such any condition for normal. But we have the equation of normal in parametric form. So let's write this. The equation of normal is ax sec theta minus by cosec theta is equals to a square minus b square. If this equation is a normal, then this equation has to be of this form. That means Lx plus my is equals to n. If I am saying that both these two equations are same because this is also normal and this is also a normal. If these two equations are same, then their coefficients have to be same as well. That means a sec theta by L, if these two equations are actually same, then minus b cosec theta by m has to be equal to a square minus b square by n. What I can do is that I can clearly see that I can find out the equation of cos theta and sin theta from here. From here, cos theta will be an divided by L of a square minus b square. Similarly, sin theta will be minus nb divided by m of a square minus b square. Now, I have got the equation of cos theta, I have got the equation for sin theta. If I eliminate theta from these two equations, then I'll get the locus. How? Squaring and adding will give me a square divided by L square because n and a square by b are common, so I'm going to take them on the other side, or let's keep them here. N square a square minus b square square plus n square b square divided by m square a square minus b square is equals to 1. Now take this a square minus b square square and n square, which is the common to the other side, and hence proved. So we have proved that if this equation is a normal, then this condition is true. Let's move. Now the next concept is actually a very rare concept. It's maximum number of normals that you can draw from a point. Now this concept is a very rare concept that anyone teaches you. So what we are going to do is that we know the equation of normal. Now we are going to derive that how many normals can be drawn from a point. So we know that this is the equation of normal. Ax sec theta minus by cosec theta is equals to a square minus b square. Now I want to know that how many normals I can draw from this, from any specific point. So let's try to write it down in some other sense. Look what I am doing. Ax, this is sec theta, that means 1 upon cos theta. Look what I am writing to this. To this cos theta, I can write 1 minus 10 square theta by 2 and 1 plus 10 square theta by 2, the form of cos in terms of 10 half angle. Similarly, by cosec theta, I can, cosec theta is 1 upon sin theta, so sin theta is 2 tan theta by 2 divided by again 1 plus 10 square theta by 2 is equals to a square minus b square. Now our equation is looking too messy and it's going to get messy further. So let's put tan theta by 2 as t. Now I am simplifying. Look, ax 1 plus t square of 2t minus by 1 plus t square of 1 minus t square is equals to a square minus b square of 2t multiplied by 1 minus t square. Now this is some polynomial in t and we need to simplify it. So let's simplify it. What I am going to get is ax 2t plus 2ax t cube minus by, and then 1 minus t square, 1 plus t square is 1 minus t to the power 4. So minus and then plus by t to the power 4, and that equals 2ta square and then minus 2t cube a square and then minus 2b square t and plus b square t. And this is, okay, there is a 2 and then this becomes t cube. So this is the simplified form. Now again it's a very weird equation, so let's try to write it in the actual polynomial form. So by t to the power 4. Now I'm going to collect t cube terms. So t cube 2ax, this term, then this term, plus 2a square and then this term, minus b square, minus 2b square. Now there is no t square term. After t cube there is no t square term. Now t terms, t of 2ax, this term, is there any more t? No, that's it. Yeah, there is one here. Minus 2a square plus 2b square. Okay, so you have accounted for all the terms. Let's count the number of terms in such cases. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. And are we missing anything? 1, 2, 3, 4, 5, 6, 7. Okay, yeah, the last term that I need to write, that is minus by is equals to 0. This equation is actually a fourth power equation in theta by 2. That means there are 4 different roots possible. To this equation, there are 4 different roots possible because there can be 4 different values of t at max. So at max, there can be 4 different values of theta from a specific point. That means there are 4 normals that you can draw from any point. Let's say you pick h comma k any point, you write the equation of normal, and if you solve like this, that means there are 4 normals that you can draw. Now what is the condition to draw 4 normals? For example, any general point can't be used to draw 4 normals, and you're not going to do this much lengthy effort for each and every point to check. So there has to be some different things. Now let's see. I know one thing, that is tan of a plus b plus c plus d is actually, it's given by summation tan A, that means 10 or taken only one, minus summation tan A, tan B, tan C, that is sum taken 3 at a time, divided by 1 minus summation tan A, tan B, that is sum taken 2 at a time, minus, plus multiplication of roots, that is tan A, tan B, tan C and tan D. So this is the formula for, this is actually the formula for opening of 4 triangles in this form. Summation tan A is actually sum of roots taken one at a time, because tan A is root. If I write this thing like this, tan of let's say theta 1 by 2 plus tan theta 2 by 2 plus theta 3 by 2 plus theta 4 by 2, plus theta 4 by 2. This is actually, these are the roots of the equation: tan theta 1, tan theta by 2, tan theta 3 by 3 and tan theta 4 by 4. If these are the roots, then here the values will be roots. Summation tan theta 1 by 2, that means sum of roots. So sum of root taken one at a time, let's write it as S1. Sum of roots taken 3 at a time, 1 minus sum of roots taken 2 at a time, and then multiplication, that is sum of all of them, S4. So S1 minus S3 divided by 1 minus S2 S4. Now let's put the values. Put values of S1, S3, 1 and S2 and S4. What is the value of S1? The value of S1 is minus B by A. So that is, the value of S1 is minus of this whole thing divided by BY. S2, sum of roots taken 2 at a time is 0 because there is no t square. S3 minus d by A, this is d, so d by by, this whole is d, and then S4 is minus by divided by by, that means S4 is 1. Now look carefully, we have S2 0 and S4 1. If I move to the next slide, if I put the values, S2 is 0 and S4 is minus 1, that means whatever be the numerator, we don't care, it's at least non-zero. The denominator is 0, that means tan of this thing is coming infinity. Sum of all the roots, sum of all the angles is coming infinity. That means theta 1 plus theta 2 plus theta 3 plus theta 4 by 2, this is actually an odd multiple of pi by 2. Or if I take theta 1 plus theta 2 plus theta 3 plus theta 4, this is actually an odd multiple of pi. Now what is this? This says that if you draw 4 normals from 4 different parametric angles, if the sum of their parametric angle equals 2n plus 1 pi, that means they are concurrent. And from that concurrent point, if you look in the reverse direction, you can draw 4 normals. So this is how interesting this concept is. I'm repeating it again. Theta 1, theta 2, theta 3, theta 4. These are actually parametric angles that are lying on the curve. Okay? If sum of all these parametric angles is an odd multiple of pi, that means all these 4 normals are concurrent. Now, picking up this concurrency point, if you look in the reverse direction, that means from this concurrent point or from that h comma k, you can draw 4 normals if and only if their parametric angle sum is odd multiple of pi. So this is actually a very rare concept. You may not find it anywhere. So if you have understood here, that's very good. But just go through it once again and try to solve it by yourself. It's very simple. We need to just put tan sine and cos in terms of tan and do the simple polynomial simplification. Let's move to the next point, that is equation of chord whose midpoint is given. So equation of chord whose midpoint is given, suppose this is a chord and its midpoint is x1, y1. So its equation will be, if you know the midpoint, you can find out the equation of chord by t is equals to s1. Where we know what is t and s, they have their as usual meanings. So t is equals to s1. This is actually a general thing. It is valid for circle as well, parabola as well, ellipse as well, and hyperbola as well. So pair of tangents, equation of whose midpoint is given, equation of chord, these are actually general things. So you can apply them in any chapter of conic. Let's check our concept for this. We need to find out the locus of midpoint of all the chords of ellipse that are parallel to this line. So locus of midpoint of chord, that means I am going to first write the equation in terms of midpoint. So let's say that h comma k be the midpoint, then my equation is t is equals to s1, that means hx divided by a square plus ky divided by b square minus 1 is equals to s1, that is h square by a square plus y square by b square minus 1. Minus 1 cancels out. We got hx by a square plus ky by b square is equals to h square by a square plus this is k plus k square by b square. Now this, we need to find out the locus such that they are parallel to this line. That means this line and y is equals to 2x plus c are parallel. If they are parallel, then their slopes have to be equal. That means 2 is equal to slope of this line. What is the slope of this line? The slope of this line is minus h by a square into b square by k. That means this equation is k is equals to minus b square by 2a square h, or if I write it in x and y terms, then we get y is equals to minus b square by 2a square x. So this is the required locus, which actually is a straight line.
So that's it for this part. I hope that you have understood both the things, that is the pair of tangents and the equation of normal. Remember that the condition that I have derived for the 4 normals from a point, it's very important. In many of the books or in classes where you are studying, teachers don't usually tell this thing, but this is also an important part and an important derivation. So please keep that in mind. Remember that condition as well. Now in the next part, we are going to start with the pole, polar form and diameters. Stay tuned.